Module 1, Lesson 16, Translations. This is another basic rigid motion. So a translation is going to map line to line, ray to ray, segment to segment, and angle to angle. Our translations are going to be distance preserving, so segments are going to have equal length, and it is going to be angle preserving, so our angles are going to have equal measure. Now, a translation is a transformation that maps all points the same distance in the same direction. Now, this makes it different from our other transformations. Rotations, remember, turned it around a circle, and reflections flipped it over a line. A translation, remember, is just a slide. So we are moving all of our points the same direction and the same distance. So our size, shape, and orientation remain the same. So, of course, a translation is an isometry. That means we have congruent segments and congruent angles. We are distance preserving and angle preserving. Some vocabulary for us here. A vector is a directed line segment. Okay? It has both length and direction. So it's going to tell us how far to move our figure and which direction to move our figure. Now, a vocabulary that we already know is parallel. Lines are parallel if they do not intersect. And the thing about our translations here is that because everybody is moving in the same direction, the same distance, all of our vectors here are going to be parallel to each other. So they are not only congruent as far as distance goes, they are also parallel. That leads us to our major concepts. When we translate a figure, we construct, that means compass and straight edge, we construct parallel lines. We want them parallel to the vector and through the vertices of our original figure. And then we would simply measure distance away. So this right here discusses how this works. We have a vector AB. And we know that we are moving our figure from point A to point B in this direction and this given distance. So for any point that is on our line AB, so we are just going to extend this out here, right? Segments make up part of a line. So there is our line AB. Any point that is on this line simply moves this distance. So we would move A to B. Now what happens when we have a point not on this line? So we have, let's say, point P here. Now we know that we are going to need a parallel line, which we're going to have to construct. So these two lines are going to be parallel. And what happens is that point Q is going to form a parallelogram here. So we know we need to move this distance. This is our distance AB. This is going to be point Q. So this distance is congruent to this distance. And what we end up forming here is a parallelogram. And we will see how to do that in this example down here. So we will go to our construction application and do examples of how to construct parallel lines using a parallelogram and circles. We will also construct parallel lines using congruent corresponding angles. And to do that, we are going to have to construct congruent angles. So both of these instructions are here. This is based on the converse of the corresponding angles postulate, which says if corresponding angles are congruent, then my lines will be parallel. We will also do an example of constructing parallel lines using perpendicular bisectors, because we know that if two lines are perpendicular to the same line, then they will be parallel. And we will talk about finding the center of a circle. We have a theorem that says in a circle, the perpendicular bisector of a chord contains the center of the circle, and we are going to be interested in finding the center of a circle. A chord is simply a segment whose endpoints are on the circle. So what we are going to do here is we are going to draw a chord anywhere that's not a diameter. We are going to construct the perpendicular bisector of that chord. We know how to do that. And why do we do that? Because we know that every point on the perpendicular bisector is equidistant from the endpoints of the segment. And then we will construct the perpendicular bisector of our new green segment here. And if it's perpendicular and bisects, then that means it's going to be at the midpoint, which is going to be the center of our circle. So let's go do some constructions. We are going to construct parallel lines using circles to create parallelogram here. Our first instruction says to draw circle P with the radius AB. Now think about what we're doing here. We're trying to construct a parallelogram that goes just like this. So the first thing we need to do is figure out this length right here. And how do we measure length? We measure it with a compass. So we measure length AB, and then we come up here to point P, and we know that we want point Q to be that far away from point P, but where do we put it? We don't know. We could draw just that much of the circle, right? Because we know that it needs to go out that direction, or we can draw the whole thing. Doesn't matter. But we know that it's going to be right in here somewhere. And now the next thing we want to do is we want to create this line over here. We need this other side of our parallelogram. So how do we do that? Well, we draw another circle around B, only this time we're using this length, right? This is the side of our parallelogram here. So we are going to go around B. We know that point Q is this far from B. Now we could just draw right up here where we know that point Q needs to be, or we can draw the entire circle. That's fine as well. But we now have an intersection point that we can label as Q, and we now have a parallelogram. See our parallelogram here? And parallelograms are parallelograms because they have parallel sides. What that lets us do is to draw our parallel line. So we can say that these two lines are parallel. That line PQ is parallel to line AB. And we can also say that length PQ equals length AB. Because when we are translating our figures, we are moving our points the same distance in the same direction. So we moved point A to point B, a given distance, and we move point P the same distance to end up at Q. And we do that on parallel lines. So we have translated basically segment PA here, translated it over to become segment BQ. Our next construction is to construct parallel lines using corresponding angles. Our theorem, our converse of our corresponding angles postulate, says that if corresponding angles are congruent, then your lines are parallel. So we want a line parallel to our given line that goes through point N. So the first thing I'm going to do is I choose any point on my line and I name it H. And the reason that I'm doing that is because I need a transversal. So I draw my transversal here. And now we have this angle right here. And I want to construct that angle up on N. Well, how do we construct an angle? With a compass, of course. So I take my compass and I measure off any distance here. We just cut across our angle, right? Because we're measuring our angle. And then when you are copying an angle, constructing a congruent angle, you simply repeat the steps on the ray that you drew. So there we go. I did that. Now don't forget, constructing an angle is the one where we change our compass setting. Because now we have this angle, but we need to measure this distance right here. And so I already have this first point, but I am going to take my compass and set it to this distance because I'm measuring a distance, right? I measured that distance. Now I just simply come up here to my new angle and do exactly what I did on the original angle. And now I have this point through which I can draw my parallel line. So now these lines are parallel and these angles are congruent. Actually, it's the other way around. These angles are congruent, therefore my lines are parallel. Now we are going to construct parallel lines using perpendicular bisectors. This is another good way if you can remember how to do it. Perpendicular bisectors are extremely useful. So we have our line here. This is L1 and our point that we want the line parallel through. So we simply take our compass and we know how to construct a perpendicular line from a point not on the line. I create my segment because that's important, right? And then I just use my compass setting and construct my perpendicular bisector. Right? So now I can draw a line and we know that this is perpendicular to L1. So this is L3. Now I have a line that is perpendicular to my original line, which means all I have to do is construct a line that is perpendicular to L3 through point A. And we can do that as well. We know how to do that. From a point on a line, I simply make a segment, right? I now have a segment here, and I'm going to construct the perpendicular bisector of that segment. Set my compass length, crosses down below, crosses up above. Go to the other side, crosses up above, down below, and now simply draw my line through there, and this is L2. So we can say that L1 is parallel to L2. Now, if we wanted to translate our figure on any of these, we would just use our compass to measure the distance that we wanted it to move. So because this is perpendicular and this is perpendicular to line L3, we have two lines perpendicular to the same line. Our theorem says they are parallel. Now the last thing we're going to do is to find the center of a circle. And our instructions tell us the first thing we want to do is to draw a chord. Any chord anywhere on our circle that is not a diameter. Because what a chord does is it gives us a segment. Now, why do we want a segment? To construct a perpendicular bisector, of course. So we simply measure our segment. And construct the perpendicular bisector of that segment. Now, why do we want the perpendicular bisector of this segment? Because we have a theorem that says the perpendicular bisector of a segment contains the center of the circle. And what you see here is we have drawn a diameter. So we now have this diameter across our circle. Because this is a perpendicular bisector, right? We know it's perpendicular. We know it bisects. That means that any point on this line is equidistant from the endpoints of this segment. Well, what do we know about the center of a circle? It is equidistant from all points on the circle. So it makes sense that our center would be on the perpendicular bisector. Well, how are we going to find the center now? Well, we have a segment. And how do you find the center of a segment? That's right, perpendicular bisector. So I'm going to measure my diameter. And above and below. And now I have perpendicular bisector, which means that right here, because this is perpendicular and bisects that, this has to be the center C of our circle. So perpendicular bisectors are really very useful. A good concept to understand. So I hope you enjoy constructing parallel lines.